Hello, gals and guys. Mr. Ambrose here with a video on related rates. I do apologize that my Chromebook wasn't working today, so this video is meant to go over the problems that we looked at in class, which was just a continuation of related rates types of questions. So the first problem that we looked at, there were two. First of these was the following. We have, in this example, a 17-foot ladder is leaning against the wall. If the bottom of the ladder is pulled along the ground away from the wall at a constant rate of 5 feet per second, how fast will the top of the ladder be moving down the wall when it is 8 feet above the ground? So with the related rates problem, the steps can still be the same. You first perhaps can draw a picture, and then from there identify the variables that are key for the problem. So this is a typical related rates problem, the ladder falling down the wall. And so to kind of see this in action, here is a simulation where we have our ladder leaning up against the wall. And unfortunately, thankfully, I guess there's no one on the ladder, but unfortunately this ladder is just going to fall down. And so the ladder will be looking like this as it falls down the wall. And the shape that hopefully we see here, right, is a shape of a right triangle. So I'm going to draw that shape in my notes, and then we'll start trying to identify variables relevant to this particular problem. So here is my wall, the ground, and my ladder. And okay, what are we given? We are told the ladder is 17 foot long. So that's the hypotenuse of this right triangle. So I'll label that as C, and we know C is equal to 17. We have here that the ladder is being pulled along the ground away from the wall at this rate of 5 feet per second. So hopefully we would agree that that is corresponding to this leg of a right triangle because that's the ground. And so because of that, I'll label that side B. And we're not told exactly what the length of B is, but we are told the rate of change for that side B. And that's the rate of change with respect to time. So I'm just going to write off to the side here that we know that dB dt is equal to 5. And now, if I go back to perhaps this picture here, as the ladder is falling away from the wall, since this side is getting larger, that side is increasing, and so this rate of change I'll leave as just a positive 5. And we want to find out, once again, how fast will the top of the ladder be moving down the wall. So that's going to correspond to this particular side here. And we're going to want to find that rate at which this side is perhaps changing. So dA dt is what we're going to solve for. And we're going to want to do this when the ladder is 8 feet above the ground. So I'll put that value for 8 in for that leg there. All right. So that's all the information from the problem that I gleaned out from it. And so we're dealing with the three sides of our right triangle. And so the formula that will relate the three sides of a right triangle will be the Pythagorean theorem. A squared plus b squared is equal to c squared. And so as with the related rates problem that we did yesterday, and hopefully you were able to do for homework last night, we now can take this equation and we can just start deriving it with respect to time t. So the derivative of a squared would be 2a times dA dt. The derivative of b squared, oops, my Pythagorean theorem, it's not this here, sorry. A squared plus b squared equals c squared. So I'm sorry, getting back to the deriving of this equation. The derivative of b squared, that will be 2b dB dt. And then this should equal the derivative of c squared with respect to time, and that would be 2c dc dt. All right, so now we've derived this here, and we can start trying to solve for the particular rate, which is this rate dA dt, which is right over here. But to help with solving this equation, because every term has a 2 in it, I'm just going to divide through by 2. And I'm going to actually continue this on the next page, and I'll rewrite what we have after having divided through by 2. So we have a dA dt plus b dB dt is equal to c dc dt. And now, again, we're going to solve for dA dt, and I'll do that by starting plugging in values for the variables that we have here. So the value of a, we were told, is 8, right? Because that is the height over here at the time we're looking for that rate with the rate of dA dt. Now b, we're not told exactly what that is, but when this happens, there usually is enough information in the problem to allow you to solve for any missing variable. And the way that we can solve for b is that we know this leg is 8, the hypotenuse is 17, and so we can solve for b by using our Pythagorean theorem. And so if we do that, we would have 8 squared plus b squared is equal to our hypotenuse squared. And we can, just go about solving for what b is. So I'll subtract both sides by 64. And we'll get b squared is equal to 225. And when we take the square root of both sides, we get that b is equal to 15. Now, you might have also recognized this as a Pythagorean triple. So if you recognize that, you wouldn't have to show the work of, finding and solving for b. You can just write it in. All right, so then continuing along, dB dt, we were told was this 5. All right, so I'll put that 5 there. And c, the hypotenuse, we were told was 17. But now, dc dt, we were not told exactly what dc dt is. dc dt should correspond to the rate of change in the length of our ladder or our hypotenuse here. And again, since we're not told exactly what that is, there must be a way to sort of figure out or surmise exactly what dc dt should be equal to. And the thing is, in the ladder problem, typically this ladder is just a static ladder. It's going to stay the same length throughout the entirety of the problem. You especially hopefully see that right here. Again, this ladder is going to fall down, but the length of that ladder is not changing at all. And since that side length is not changing, that means the derivative dc dt must equal 0 to correspond to the fact that this side length does not change at all throughout the problem. So dc dt we can say is equal to 0, and I'll plug that in here. And now we have enough information here to solve for what dA dt is. So the right side becomes 0, and then 15 times 5 is 75. And if we subtract that over, we get negative 75, which means that dA dt is equal to negative 75 over 8. And in this question, I didn't ask for the units of measurement, but the units of measurement for that rate should be the same feet per second that we see for the rate of dB dt. So I'll just write that in there. And then the other thing, as perhaps just a little check here, hopefully this makes sense. Notice dA dt has a negative value to it. And that's because, right, this length between the height of the ladder to the ground, which is that part of the wall, as time goes on here, right, that length is getting smaller. So it makes sense that dA dt would be negative to denote that things are decreasing.